All right. So Michael Sinatra is up to speak with us, or speak to us about what he calls feeling the Brady Bunch's pain, which is the consolidation of the SNet and ANI networks.
Okay, thank you. Excuse me. Thank you. I do realize that I'm the only thing standing between you and the Aaron update, so I'll be very brief. Sorry, Mark. No, I like the Aaron update. I really do. Thank you. All right, this is what I'm going to talk about. Basically, we had two networks that we had to put together. We had an ANI prototype network that was a grant-funded network that was a full nationwide 100 gig network. And the purpose of the network was to basically say, if you give 100 gig to the scientists, will they come? Will they be able to do 10 times the science at 100 gig than they were able to do at 10 gig? And the answer is basically yes. It's kind of a simplistic answer, but there are both qualitative and quantitative benefits to science by increasing the bandwidth. Science is still very much bandwidth constrained. So having demonstrated that, the idea was, now let's take the 100 gig network and give it to the scientists by merging it into the production network that we have in ESNet. So what were the two big things that we had to do? We had two networks that were logically separate, and they were actually BGP peered with each other in the same way that Internet 2 and ESNet might peer with each other, or actually do peer with each other, in the same way that we might peer with some of your networks out there too, at different areas. And the big difference, if you look at the table here, was we had different IGPs running in the network. That was going to have to get fixed before we put them together. And in particular, the old network, or the existing production network, had OSPF still doing IPv4 and ISIS doing IPv6. ESNet's very old, and we've been running ISIS under IPv6 for a very long time, and the idea was to eventually get rid of that and try to make it a single merged IGP. We also had different both SDN, and we originally called SDN Science Data Network, but it really was an SDN technology using our Oscar software, and IP were routed over separate links. We were going to converge those in the 100 gig links. So there were a few things to do, and there were a few important points. And you can go ahead and read these. The slides are available online. But one thing I want to stress there is not only didn't we want to put the network down, but we didn't want IPv6 to be treated any differently than IPv4. So we wanted to have SLA parity. So the first big issue that we had to do before we merged the two networks was to decide whether to merge the IGPs or leave things as they were. And I'm going to kind of make a little confession here. I have about 30 minutes worth of content and about 20 minutes to do it. And I only wanted to actually take 20 minutes for this talk because this part's really boring. And so I don't want to actually have to go through it. So instead, it's all on the slides. All you have to do is read the slides when you're about to fall asleep or something like that. But this actually talks about the whole decision process we went through. So we had to decide whether to merge the IGPs. There were pros and cons to doing that. We had to decide when we were going to do it. There were pros and cons as to when we did it. Do we do it before we're merging the networks? Do we do it during, or do we do it after? We had to decide whether we're going to use ISIS or whether we're going to use OSPF v2 and v3 and converge around that. Pros and cons to that, obviously. We decided to do ISIS. We had to decide whether we're going to use multi-topology or single topology ISIS. There were pros and cons to that. We decided to do multi-topology. How do we do the switch once we've decided to switch to multi-topology ISIS? Because not all router vendors have compatibility modes where you can switch on the fly between single and multi-topology. And if you're already running IPv6 in production, you can't just switch from single to multi-topology because you will lose your IPv6 routes as one router goes from single to multi and the other router is still at single. This router's not going to see the IPv6 routes. So you're going to start black holing IPv6 traffic, and remember our SLA parity says we want IPv6 to be treated as a full production service, just the same way that we treat IPv4. So we couldn't just do this switch as a forklift. We had to do something else. Because not all routers had compatibility mode, we actually had to add OSPF v3 as a temporary protocol just to route IPv6 while we were switching to multi-topology. And I mentioned, I make a reference to Caltrans here. The California Department of Transportation once built the highest freeway ramp in all of California just as a temporary measure so they could work on the one that was down below it. That was just to let traffic go unimpeded as they were doing construction down below. And it took 10 years and a couple extra $1 billion just to do that. So Made me think that I was being Caltrans here just by turning on OSPF v3. But it turns out it was really easy to do because the OSPF v3 configuration in most routing platforms is very, very close to the ISIS IPv6 routing configuration. And all you have to do is programmatically go through and scrape all your routers, generate OSPF configs, slam them in, and then do a bunch of stuff to compare the routes that you're seeing in ISIS and OSPF. That yielded very interesting results, as it turns out. And I'm going to give away one of my lessons learned here and say that when you turn on OSPF v3 and you've already been routing IPv6 and ISIS for a while, OSPF v3 is going to show you some interesting misconfigurations that you may have had on some of your point-to-point interfaces. ISIS won't catch those because it's running at layer 2. It's just forwarding this as another address family, another TLV type. Whereas OSPF v3 is actually relying on the layer 3 existence of the IPv6 configuration and the layer 3 consistency of the IPv6 configuration. It's going to show you problems. And so it's very important if you're running ISIS with both address families to have some sort of BFD capability. And I'm not talking about Bradford Regional Airport, I'm talking about bidirectional fault detection when I say BFD. And so BFD is very important. Not all router vendors support it, both IPv4 and IPv6. And so I want to basically tell routers, especially if you're a router vendor whose name begins with J, that it's very important to support both IPv4 and IPv6 BFD and integrate them with ISIS so that you can actually withdraw routes when you have misconfigurations and broken interfaces. Okay, so we had one other decision we had to make, and that has to do with sort of one-offs, and you can read about it in the slides. I'm not going to talk about it too much, but it basically has to do with the way for our sites that don't carry a full table, how do we announce default to them? And we have special default prefixes. And the way we were carrying those was in both our IGP and an IBGP, and we needed to clean that up. That was going to induce some risk that we might have some individual site outages. And it turns out that did happen because of some, like I said, some really weird one-off configurations that we had. But overall, the whole process worked very well. So this is a visualization of the decision. It's not a true decision tree in a game theoretic notion because there's no payoffs. I just sort of talk about, the pros and cons. But you can see how the decisions that we made led to other decisions and actually led to more work, particularly because we chose that the path that's all the way on the right-hand side. So you can see how that leads to a bunch of other complexities that we have to get through just to put the IGPs together in the way we want to without causing any traffic black holing. So then we had to do it. We had to create a plan, a very detailed plan, which you can see I did it in a Google Doc here. And so that was kind of interesting. I left a little space for everyone. I had major steps and detailed steps and remarks and things you do. And I had a little space for everyone to sign up so they could actually say, I'm going to take this one particular step. And we had a very interesting, maybe I should talk with the folks at Google, very interesting failure because I know all my coworkers immediately rushed to sign up and do all this work. But when I logged in, their names weren't there. It was just blank, like the way I had left the document days before. So I assume there was some kind of Google problem that caused that. I'm not sure. Anyway, what ended up happening is I ended up doing a lot of the work. Now, this is kind of an important lesson learned, which is you don't want any one engineer in your network, no matter how brilliant he may be, to do all this work. So what we ended up doing is I did a lot of the work and I had a lot of people looking over my shoulder. When we actually ended up doing the merge of the networks, I managed to do it in such a way that I had the timing scheduled so that I'd be on travel for a good chunk of the work and so that other people would actually have to do the work, but we'll get to that in a second. Here are all the steps we did, so you can read through those. And I already talked about the outcome and the need for BFD in both OSPF, in both IPv4 and IPv6 when you're running ISIS. And so now we've merged the IGPs, we've put them together, now we're going to merge the networks, okay? And how best to do that with, again, not causing any downtime on our production services. We could take the prototype network and shut it down. We didn't have that many production services on that, so we were able to move the production services onto the existing ESNet4 network. That gave us the opportunity to do, for a short time, some break-and fix stuff. We could also move our SDN circuits, our Oscar circuits, but we had to coordinate those. Those were not, they didn't have to be total 100% uptime, but we did have to coordinate when we were moving those circuits. So, given that, we actually went through and started to merge the actual routers into the new network. And we're taking a different platform, ALU, and putting it into a network that's predominantly Juniper. So we had to rewrite a lot of our tools to make sure they supported ALU. And we went through a bunch of steps, which you can go ahead and read through. What I'm going to do is give it to you in this miraculous graphical format that uses the metaphor of the Brady Bunch. This is why I use this in my title. We need to take these two networks and somehow make them a family. So in this diagram, the male Bradys represent the existing ESNet4 Juniper routers, and the female Bradys represent the Alcatel-Lucent routers in the prototype network. And I had to add Cousin Oliver and Alice to sort of make an extra pop. This is obviously a very stylized diagram. If you want to see a real diagram of ESNet, you can basically look at the diagrams of Internet 2 from the previous presentation, because as Chris pointed out, we share the same physical footprint. So this is what they looked like when they were actually all plugged in. Now, the thick red lines are 100 gig links, the red routers are the ALU routers in the prototype network, and the blue routers are ESNet4, and they are connected with multiple 10 gig links. Those are the thinner blue lines. You see some black, thin 10 gig lines. Those black lines are lags, and they are eBGP peerings between the two networks. So what's the first thing we do? We build a bunch of configurations, and we had to rebuild our configuration templates, which are YAML templates. Then we had to generate configurations for each of these ALU routers. When we did that, we put them on the flash and we did a big reboot. We basically rebooted all the routers at once. And what that did is it put them into a situation where they weren't yet BGP meshed, IBGP meshed with the rest of ESNet4, that's why they're gray. But they did bring up ISIS adjacencies along all of the 100 gig links. So the 100 gig links came up immediately. We just costed them out of production, so they weren't actually routing they weren't actually traversing traffic. There was routing happening, but there wasn't any traffic going over them. The next thing we did, you can see we added some links between the ALUs and the Junipers, between the male and female Bradys. Those became ECMP links. That was another decision that we made. I won't really go into it. We didn't have any good reason either way, but we felt like maybe ECMP would reduce some of the variables that lags put in. We just kind of wanted to try different things. So we wanted to add links because we were concerned about bottlenecks along certain 10 gig portions of the network. As we brought the 100 gig portions up, there might be too much funneling of traffic into 100 gigs. So we had to be very careful also how we did our IGP costs as well. So now what we start doing is going through and meshing the routers, connecting them up. In this case, what we're doing is taking the different ALU routers. They're becoming part of the ESNet4, which is now becoming ESNet5 IBGP mesh. And at that point, we now have the full network in place. So we have IBGP routing and we have ISIS routing with all of the routers in the network. The only thing that's not happening here is the 100 gig links aren't costed into place. And with the push of the button, now all of a sudden the 100 gig links are now costed into the point where they're actually routing. Now we have a full network. The key is here we have to now get rid of the 10 gig links because that was part of a level 3 service that they were providing to both us and Internet 2 that they were actually going to resell to another customer, so we needed to get rid of that. So we cost the 10 gig links out of production, and then we get rid of them, and now we have our new ESNet5 network, and I think it took me about a minute or two to upgrade the network just there. So what happened when we did this? What were some of the lessons learned? One of the most important lessons learned was having a plan, also having the right people and having lots of people do it. Now this is the group of people in ESNet that worked on this, and I want to point out that as you go back and forth, there's really no reason to assume that my replacing Cousin Oliver has any significance. What I really did here is just reproduced in groups the different things that people did. So you see Yvonne Hines, for example, a longtime NANOG attendee. She and I did a lot of the routing and IP addressing. You can see over on the left, Chris Tracy and Patrick Dorn. They both did a lot of the optical stuff. So we had a lot of people doing a lot of different things in this network. Now, one of the other major lessons learned was sometimes routers have bugs. Who knew? So in this particular diagram now, we've got the full ESNet5 in place. We've got 3 routers, 2 Juniper routers, which are represented by the 2 Brady kids there, and an ALU router, which is completely part of the network now, which is represented by my colleague Joe Metzger. Joe doesn't really like this slide because he thinks it makes him look like he's the father of the 2 Bradys, which I don't understand why he thinks that. But one day, we had a situation where we have a lot of these ECMP links connecting the ALU routers, and what I don't show there is that Joe has a couple 100 gig uplinks coming out of him, And so he's got all these 10 gig ECMP links coming into him so that he has enough bandwidth to go to the downstream Junipers. And one day we realized we had to replace a line card in Joe. So that line card served 2 of the links right there of the 4 ECMP links, so we had to cost those links out of production. As soon as we costed the links out of production, Marcia, or whoever that is, started routing traffic the wrong way. Even traffic destined for Joe's loopback, she was routing over there to Bobby. I don't know if that's Bobby or not, but let's just pretend it's Bobby. She starts routing it to Bobby. Now, when you look at Marcia's routing table, it looks right. It says, all this traffic, all these addresses, all these routes, I'm forwarding out the ECMP links, the remaining ECMP links. That's what it says in the routing table. But when you look at what she's actually doing, she's forwarding the traffic the other way. Now, how did we know what she was actually doing? We looked at NetFlow. You can see it in NetFlow. The packets are going out the wrong interface. So this is very interesting because the routing table shows everything is right. NetFlow shows that it's wrong. And the actual experience of the fact that we can no longer get to Joe's loopback also shows that she's doing something wrong here, that Marcia there is doing something wrong. So what we did is we said, well, okay, we might as well just pull the line card now because we can't see any traffic here. And as soon as we pulled the line card, everything went back to normal. So my conjecture here is that Marcia did a fib update, and all of a sudden whatever was wrong with the fib got fixed. It didn't change the routing. The routing table hadn't changed at all, but the fib update happened because the interfaces dropped link. So, we said, okay, let's put the new line card back in, let's put the links in, costs out of production, nothing goes wrong. We put the links into production, nothing goes wrong. So just that one little part caused someone's fib to go wrong. This happened 3 different times at different parts of the network when we were doing different pieces of maintenance. So we found that there were some interesting vagaries that happened with ECMP links, and that caused some of the routing to have weird things. Joe Metzger incidentally thought that I had screwed up the IGP when I did the IGP merge, and so it was obviously in my best interest to figure out what Marcia was doing there when she was forwarding traffic the wrong way. And it turns out it was actually the router's fault, not my fault. I'm happy to report. So what other lessons? The importance of planning is really good, having a detailed plan. This is just one page of the plan, and this is now in a wiki, I didn't put it in a Google Doc this time, of actually merging the routing of the 2 networks. So you can see how, how much stuff there is in there, and really what we ended up having was a lot of different people working on this. And because you have a written plan, you can actually, anyone can pick it up. If someone's out or if someone's traveling, someone's at NANOG like I was, you can have other people pick it up. So a lot of those steps happened when I was gone, even though I was one of the people kind of leading the plan, and it was really easy to be able to do that. The other really interesting part about planning is that as you write a plan to do something like this, you actually begin to think through the process so carefully that you find dependencies and you find other things. You find things that are going to go wrong before you actually do it. And it's a good way to kind of fix the things that go wrong before they even go wrong. So I think a plan is extremely important for that. And it's actually amazing how well things did work in the end. So with that, thank you very much. That concludes the presentation, and I welcome any questions. Thank you.
All right, thanks, Michael.